everyone, welcome back to another stretch of Dr. Erin Explains the Universe. We took a hiatus for a little bit to do some of these episodes, to record some of them, get some questions answered. I did some live streams. So welcome back. We've got more science. We're going to be doing a lot more science because I've got a lot of questions from people. And we'll be doing a lot more different sci-fi that we've not explored yet. So in this episode, I want to talk about the life cycle of stars. And the reason for that is because in science fiction, we see a lot of things thrown around like supernovas or black holes or red giants or main sequence stars. What does that mean? Where in the whole solar life cycle do those fall? And yeah, so I'll just be giving some context for that. So first of all, when we talk about a solar life cycle, basically we're going to be talking about the birth of a star all the way through its life and to its death. Now, there's lots of different types of stars out there, and so we're going to be discussing kind of where each of those kind of fall off, where they branch off, and hopefully it'll make sense. And then you'll see it cycles around and it starts all over again. Circle of life, that sort of thing. So to start with, I've talked before about kind of that our universe has a lot of dust and gas in it. So when we're talking about, if you remember the cosmological address idea that we have star systems, we're going to be focused on stars. And so within galaxies, within our universe, there's just a lot of dust and gas floating around. And when you get a big cluster of dust and gas, we call those a nebula. So it's just a big cloud of dust and gas, nothing of any significance or importance other than, I mean, there's stuff we can learn from them, obviously, but it is just dust and gas. And over time, those start to coalesce and the dust starts to snowball. And basically what you can kind of picture it that you get kind of particles of dust collide into one another, gas particles kind of collide into one another. They're not fusing, but you know, they might just sort of attach, and then they build up gravity over time, and they start to, you know, once you get a couple dust particles together, then they have a tiny amount of gravity, and then other dust particles will go, oh, hey guys, party going on. So you get all these dust and gas particles together, and you start to form what we call a protostar. Now, what's happening at that stage is, you can think friction, rub your hands together, you can feel that heat. Same thing happens when you get a lot of dust and gas particles. They start to rub against each other and you start to get a lot of friction, so it starts to heat up. And all this gas and dust is still falling in. You can imagine, again, this snowball effect cascading on this dust and gas, so it's getting larger and larger and larger. As all this matter is continuing to fall in, that's what we get a protostar from. So it's not ignited, it's not become a star yet, but it's starting to get a kind of a hot ball of dust and gas. Now, this is going to be one point where it branches off. So we have our nebula, then it starts to glob together, and then we get our protostar. Now, if enough dust and gas falls and you just kind of run out before a star is born, then you can imagine you just have this kind of hot dust ball, kind of dust and gas ball, kind of like Jupiter ish, you know, you can kind of picture that. It's just a big ball of gas. But it's not ignited, but there's no more matter around there. And so that kind of falls off the chain, and that's what we call a brown dwarf. And so we're still trying to figure out how many brown dwarfs there are out there, but from what we've seen, we seem to think there's maybe about one brown dwarf for every 6 stars out there. So there's not a ton. Usually if you have enough dust and gas, it's going to form a star. It's not really going to get to that point, but it'll just cool off because there's no more interaction and it'll just be all sad and alone. It's really easy to anthropomorphize brown dwarfs because it's really sad. All right, so we imagine brown dwarf falls off. So ignoring that, imagine that there is enough dust and gas to keep getting hotter and hotter and hotter. And then in the core, most of the dust and most of the gas out there is hydrogen. The hydrogen will start to get really hot, and then a lot of pressure, and it'll just bunch together, and then it will fuse and it'll become helium. And when it does that, what happens is it releases energy. And so now we have nuclear fusion going on, and photons are released from that. And so once that ignition happens, that's when we have a star. A star is born. That's what we're talking about. So we have this star, and now we're burning hydrogen into helium. It's big, it's bright, it's ignited, it's a star. And so at this point, this is what we call a main sequence star. It's just going through its life. It's fusing hydrogen into helium in the core, releasing this bright energy. So main sequence stars are typically the ones that we see, that we think of. 9 out of every 10 stars out there are in the main sequence. So I'm going to show you something that's called the Hertzsprung-Russell diagram. And you may have seen this if you've taken some astronomy, but if not, this is kind of a good, cool, key thing. And you can see up in the top corner, you have bright blue, very hot, very massive stars. So these are sort of ranging about 60 times the mass of our sun, but they can go all the way up to like 200, but that's not very common. But you can take the mass of our sun, and when they get really, really, really massive, when there's a ton of that dust and gas that's fallen on and made a really massive star, it's going to burn really bright, and it's going to burn blue. It's going to be very hot. So blue hot, remember, if you see the center of a candle, it's blue near the end, near the middle, because that's where it's the hottest as opposed to the outside. So blue hot is hotter than red hot. It's kind of counterintuitive, but think of the candle. That's how I always remember it. So up in the side, we have our blue hot stars, and those are the massive ones. They're really bright. They're really hot, and they are bright. They shine. They have high luminosity, and they don't live very long. So burn bright and die young, as it were. So we have these really bright stars, and then as you travel down through the Hertzsprung-Russell diagram, then you start to get into kind of the more standard stars that we know, that we see a lot of. We call them fairly average stars. Our star is one of those. So we get sort of, you know, they're around 10,000, about 5,000 to 10,000 Kelvin, kind of yellowy. These are going to be the ones that you see a lot in science fiction, because these are the ones that we know that are like our sun. They live for about 10 billion years. Our sun has been around for about 4.5 billion years, so it's about halfway through its life. And they progress pretty normally. They're not supermassive. They're not ultra low mass. Their temperatures are pretty average, and you can see they fall right in the middle of this diagram. And then the lower down that you get, that's where you start to get the really low mass stars. So they can go as low as 1/10 the mass of our sun and still be a star. And then when you start to get lower, that's when you get like the brown dwarfs, because they just aren't massive enough to ignite. And so you get down into like this low mass area, and they are low mass. They're also very dim, and they're also very cold. And so you have this whole correlation between how massive it is, how bright it is, and how hot it is, which is kind of a cool relationship. So this is why we use the HR diagram all the time in order to classify stars. At the bottom of the HR diagram, you can see something we call the spectral classes. Now, these classes were rooted in about the turn of the 1900s. I think like 1901 was when they kind of solidified the system. And it's based on what was called the Harvard classification system. And actually, there's some really amazing kind of histories forgotten female astronomers that were a part of this classification system when they're trying to put these all together. And they came up just with spectral identifiers where they're seeing all these different color stars, and they assigned them into these spectral classes. And Annie Jump Cannon is one of them that in 1901 she kind of laid out the spectral class system that we have today. So if we talk about a G-type star, you can see in the diagram that's exactly what we're talking about. We're talking about stars that are going to live this long, that are about this mass, that are about this bright, and about this color. So when you know kind of one thing about a star, imagine I just gave you the mass of the star. You could tell me how bright it is, how hot it is. So it's really, really useful. It's awesome. But again, this is all main sequence. So this is when in the center of the star, it's burning hydrogen into helium. Okay, so this is, again, 9 out of 10 stars are on this main sequence. They're living their life, doing their thing, and then they run out of hydrogen. What happens next? Well, typically, and again, there are kind of different nuances that can happen, but overall what happens is that you burn out of hydrogen, so now you just have a core of helium. And then that helium starts to fuse into carbon. The carbon fuses into, can continue to fuse, if it's massive enough, into, I think, neon, and then oxygen, and then silicon, and then the most, if it's really, really massive, the most it can fuse into is iron. And that the reason that we stop at iron, even though there's plenty of things that are heavier than that, the reason that we stop at iron is actually has to do with a property of iron, because it's its lowest, happiest energy state. So we'll leave it at that. There's some details to it, but that's kind of why iron is the last thing, if you're massive enough. But you start to enter, as you run out of hydrogen, fusing helium, fusing the higher elements, this is when you get into the red giant phase. So stars are balanced, and we get something, we get this balanced relationship between radiation pressure, which is all the energy pushing out on the star, and gravitational pressure of everything falling in. And it's a balance that you get. And so as this star is going through its life, it's going to get bigger and it's going to turn into a red giant. Now, kind of context for red giant, when our star becomes one, it's going to expand to a red giant and its radius will reach about us. So it's going to get about as far out as where Earth is, the whole size of the entire thing. And fun fact, Titan may actually be kind of a nice place to live at that point, if we're still around, because that's like another 5 billion years from now. So don't stress about it. I don't want to give people nightmares or anything. It's going to be a very long time. Yeah, so you get to the red giant phase. And now what happens is we go through, and this is where the different masses are going to branch into the different kind of results and states of stars. So if a star is fairly low mass, fairly standard, it's burning through, it's kind of run out of its fuel, it's not supermassive, it's just doing its thing, it will just expand and eventually just kind of dissipate. And you get, and it's kind of sad. And that's it. If there's a core left over, then that's what we call white dwarfs. So you get this core that's left over after all the outer shells have kind of dissipated, and you get a core. Now when you get these big clouds of dust and gas that are left over from a star system that's died, we call those planetary nebulas. Has nothing to do with planets. It's just is kind of a long-standing thing because when astronomers would look at see planetary nebulas that were left over from dead stars, they looked like planets. They kind of had, there was a lot of colors, a lot of stuff going on. So they call them planetary nebulas, but that's just because of how they look through a telescope. And that's just the leftover gas from a star. Now, what will happen then is that gas will start to clump together and form a new star. So the cycle goes around again. And again, if there's a core left over, then you get a white dwarf from that. So that's kind of average mass, fairly normal stars. That's what's going to happen. You get planetary nebulas and white dwarfs. Now, if you have a supermassive star, or get high mass star, you go through the red giant phase, and then you start to burn heavier and heavier elements. And you're getting really big, and you're starting to push physics here. And what happens is this star reaches a point, and remember I said there's a balance between radiation pressure and gravity. You're going to reach a point where you stop burning your fuel, but all that radiation has been holding up this star. And what's going to happen is the whole thing is going to go, and it's going to collapse down onto this, and onto this core, and basically bounce back off. So we're still trying to figure out the exact nuances of like this, that's a supernova, of this supernova event, but it's really hard to model because we can't exactly replicate that in a lab. So we can just try to understand the physics of what's going on, and we can observe some of them, but we observe them at different stages. We've not been able to look at something and go, okay, it's about to happen. Well, we have in Futurama, but different. Fiction. But essentially what happens again, you run out of this radiation pressure, the gravitational force takes over, it collapses down, it bounces off, you get this huge explosion, you get bright flash of just all this radiation that's leaving immediately, and you get a really dense core that's left over because all of this has collapsed down onto it. And that's what we call a neutron star. So you have all these neutrons have been pressed together, they're pushing the boundaries of quantum physics and particle physics that are here together, and it's a supermass dense neutron star. And about what's left over is about the mass of our star. They range, there's some limits to them, but about the mass of our star, but about the size of a big city. So you could think maybe about the size of Denver or something like that. The whole mass of our star condensed to that size. If you were to take a teaspoon of it, it would weigh as much as a mountain, which is kind of a hard comparison. But yeah, so you get these supermassive stars, they supernova. What's left over is a neutron star. Now, if there's still too much mass for that, where you get these neutrons that are trying to hold up against each other, if they can't hold up, they're going to collapse further down, and that's when we get a black hole. So you get these massive stars that when they die, they supernova, big explosion, and you get either a neutron star or a black hole. But in any case, you've again expelled a ton of gas. Just this time it was a more energetic collision that happened. And so, but you have a lot of remnant gas that will eventually clump together and eventually form a new star. So you can see this whole cycle goes around again. So I hope that made sense. I hope that kind of filled in some of the gaps for you. I hope some of the images make sense. If you have any questions about this, feel free to hit me up at Dr. Erin Mack on Twitter or leave a comment in the videos. And thanks for watching, and I'll catch you next time.